Okay, so welcome to our Synergy Week. There's been a change in the audience, I would say rather significant since last week. So maybe a few introductory words are useful. This week we have more talks than in the past weeks for those who were already here in the past week. So it's important to check on the program more than in the past. The one printed outside is not yet updated, but there is the Indigo page, which is instead updated already, contains already the full schedule for the week. And you'll find useful to know there is lunch coming at 1 every day. And I think every day except today we have 11 and another talk at noon. Maybe check on the program, and another 2 talks in the afternoon with the lunch in between. All right, for the practical things, I think that's all. The other one thing I wanted to say has to do with the week, the program of the week is basically an attempt to mix different communities that are supposed to come and form a synergy about what can be done not only with muon collider experiments or muon collider related piece of hardware, but in general with muons. And the piece of hardware that go around making muon beams or what can be studied with what comes out of those muons, maybe neutrinos, maybe other things. So you will find that there is an alternation of topics every day, essentially. It's not almost a dedicated smaller workshop on a given subject. Today, instead, we have more general talks. So we start with Andrea, who's giving, even though the program entirely has to do mostly with muon collider, this week is special. There is, as I said, a lot of people who are coming from a neighbor, but not precisely from there of muon collider. So we start with an introduction to this project and the idea of the physics of the muon collider that Andrea will give us in about 1 hour. Thank you.
Okay, thank you. So, as Roberto said, this talk is going to be mostly an overview and focused on the purpose of the muon collider in terms of engineering collisions of mu plus mu minus at the center of mass energy of 10 TeV. So this is the Synergy Week, but this is not at all about synergies. It's just about what we have been discussing in the last years of the physics potential of muon collisions at the muon collider. And here there is a number of links to overviews prepared, well, these ones, all of them, by the IMCC, which is the International Muon Collider Collaboration. That is, I will comment on this later, that is this international collaboration that is pursuing the muon collider, in particular accelerator, but also detector, and physics developments. So I suppose that this talk is mostly for people who are not daily working on the muon collider, and I apologize with the others, especially to those who may have seen this talk already, and maybe also several times. So the path towards the muon collider, okay, for us means the path towards engineering mu plus, mu minus, and there are interesting ideas of different charges of muons we will probably hear about during this week. But IMCC focus on mu plus, mu minus with the target center of mass energy of 10 TeV, and so this is going to be a relatively long path, which will bring to build an ambitious, expensive collider project. And so we should better be confident that this collider, the perspective of these colliders comply with our main mission, which is particle physics. And so particle physics is essentially for me this picture, trying to understand what is inside of things, including matter, but also the entire universe, in the quest for the most simple and universal laws that rule the occurrence of any natural phenomenon. And so it's the search for the smallest building blocks of the entire universe, which are particles, and their mutual influence, which is mediated by forces. In fact, today we understand forces and particles in a unified notion, which we call a field. So in the long history of particle physics, several decades, we would like to identify what are, at least I try to identify what are, for me, the big achievements of particle physics. From the theory viewpoint, we discovered the satisfactory notion of causality from special relativity. We understood that particles do not have a positions, only detectors have a position, and detectors are operators, which then depend on time and space, and so they are called fields. And so we learned how to describe nature in terms of the dynamics of these fields, which is what we know as quantum field theory, that possesses its own, as they're called, axioms or principles, and probably microcausality is the most unique and important principle of all, which incorporates and supersedes quantum mechanics and special relativity. We are not just like applying quantum mechanics plus special relativity. Quantum field theory is more. Quantum field theory is more, is better, is more deep, and it leads us both to quantum mechanics and special relativity phenomena in a framework that so far hasn't found a contradiction. At the same time, and we worked out one single theory that is very close, not yet there, to accomplish the dream of this particle physicist girl, right? So in fact, the very idea that this dream could be accomplished, to me, just came in parallel with the development of the Standard Model, which is a theory that, in line of principle, could account for all phenomena that ever occurred in the universe, that will ever occur, and of course that we can make occur in our laboratories. And of course, you know that this monumental achievement of mankind is called the Standard Model, which is a definitely poor name for such a gigantic and important thing. The Standard Model, however, is not enough, which we can, I mean, that's for sure, but some way to spell out this can be the following. First of all, the Standard Model is built on what I like to call a practical implementation of the principles of quantum field theory, which means local Lagrangians and the perturbative Lagrangians, gauge theories and all that machinery. It's an implementation of this big microcausality quantum field theory axioms, okay? But it doesn't follow from these axioms. I like to call it practical quantum field theory. And this is the theoretical tool that we use in order to build the Standard Model. This tool is surely not complete, because if you try to apply to gravity, okay, it fails at short distances. So there is definitely a new theory breakthrough that is waiting for us in the fundamental physics, okay, which could be questioning these big principles or finding a better implementation of these principles, a different implementation of these principles that is not what we know today as practical quantum field theory and, for example, would account with gravity. Also, the Standard Model, even if you restrict yourself to this practical quantum field theory, let's say model building, you don't get the Standard Model, right? Because the content of particles and in fact of fields that you have in the Standard Model drawing is completely dictated by experiments, okay? So theory did not advance, did not become better, allowing us to say that there are other particles or that there are not other particles. It's always like it used to be, and the particle and field content of the Standard Model, in fact, in the past, came from experiments, from people engineering better devices, higher energy, better colliders that enables us to establish what is the Standard Model, starting from what is its content of particles. And so if you want to advance in this direction, we need new experiments, okay, to tell if there are more particles, and in particular, if these new particles are heavy, then by energy conservation, we can explain very easily to everybody why we need higher energy collisions. Energy conservation means that creating heavy particles requires energy, and among the many particles you will be interested in establish the existence of or establish the non-existence of, there is compelling dark matter candidates that are dark matter, not necessarily the heavy dark matter WIMP type that is of interest in this at the muon collider, but dark matter in general is one sure, almost sure need for a new particle that we have not yet observed. And then there is the third item that in fact, even if you buy the particle field content of the Standard Model coming from experiment as it is, even if you work in the practical quantum field theory methodology, you still are not able to explain why, okay, only some type of interactions the renormalizable interactions are observed. And there is, or there used to be, an explanation of this, the explanation of renormalizability that comes from something that is called the Wilsonian interpretation of quantum field theory. And this is disproven, okay, by the fact that a scalar particle of spin 0, the Higgs boson, could be a zero size particle, okay? Will not be composite, will be fundamental, will have zero size, and this is in direct contradiction with the Wilsonian interpretation of quantum field theory. And so I think it's really fundamental to check if this is the case or not only for the sake of asking a scientific question, is the Higgs composite or is the Higgs elementary? No, it has implications that go beyond that, and that are connected with our very understanding of quantum field theory. Of course, it should be mentioned that there are also, here I'm referring implicitly to what is known as the naturalness problem or naturalness paradox. And we know also that there are other ways to address this paradox that do not involve a composite Higgs, like supersymmetry. And of course, this also should be checked and can be checked at the scale of energy of the colliders that we are, of the muon collider that we are thinking about. So, there are very good motivations for continuing investigating what is inside things, trying to build the microscopes which are more and more powerful in resolving shorter and shorter distances. And the need for energetic particles can be explained very easily by the fact that, well, like any other microscope, if you want to resolve a certain distance scale d, you better use waves, okay, light waves, for example, in the case of an optical microscope, which are as small as possible, okay? And the reason is that if you have, for example, a wave that scatters on an object which has exactly zero size, or if you have a wave that scatters on an object which is very small in comparison with the wavelength, like here, the outcome of the experiment, these scattered waves that you can detect with your microscope, they look essentially identical, okay? So this is the fact that in order to have good resolution to a distance scale d, well, you better use short lambda, which in our context means large energy, because lambda is 1/e by quantum mechanics and special relativity. So the way in which I personally think to future colliders is that in first approximation they are a better microscope, which is as justified as building a better telescope, and the frontier of distance, or if you want the inverse frontier, which is a frontier of energy, is the 10 TeV scale. So, in fact, when we collide particles, okay, what really matters in order to access these short distances here is not only, if you want, the energy of the particles that you collide, but it is the energy of the partons that you collide. There is a distinction between particles and partons because particles, before they collide, they can emit radiation, which makes them lose energy. And so we know that what effectively happens when you collide a pair of particles with an energy E is a collision between some partons that you can roughly imagine as constituencies, even if maybe they are not in the strict classical sense, with a fraction of the energy of the incoming particle. And the fraction is a statistical variable that changes collision by collision. And so if you have protons colliding, you have the famous plot of the parton distribution function, which is the probability density in the space of this variable x. And you see that this parton distribution function for protons is well, it has a huge peak at very small x, which means very low energy. It has this that's called the valence peak at around 1/10 of the fraction of the energy, okay? And it's completely not populated at x equal to 1, which means that if you collide protons, you will never observe a collision of partons which has the same energy as the protons that you have collided, okay? In the case of muons, you can make a similar plot of the parton distribution function of the partons in the muons, and in particular, there is the muon parton inside the muon, and its distribution function is completely different, is sharply peaked at x equal to 1, which means that each time you collide two muons, or two electrons, a pair of fundamental particles, most of the time you will be actually observing a collision with an energy that is as high as the beam energy, okay? So most energy instead is sort of wasted at proton colliders on a statistical basis. And this is a very important thing to explain, especially to people maybe not working to colliders all their life, that a 10 TeV muon collider, in spite of having an energy which is less than the energy of the LHC, that is 14 TeV, is in fact way more effective to probe the energy scale. It probes the 10 TeV energy frontier, the same energy as the collider energy, while instead you can try to estimate what is the energy that is needed for a proton collider to estimate the same scale of 10 TeV, and this comes out to be much higher, say about 100 of TeV. Okay, so right. There is more, in fact, that we need in order to build a great microscope. Because if you really think about that, it's true that these scattered waves that come from an object which has 0 sides and an object that is small, they look very similar, okay? But in fact, they are different, okay? If you look closely enough, precisely enough, probably you cannot do it with the resolution of this plot, but still you can tell that this outcome, okay, these outgoing waves are in fact slightly different than those outgoing waves. Of course, if you go in the regime where the wavelength is so small that like the object looks very big, like here, of course there is a huge difference between this and that, but there is also some difference between this and that, such that if you have precision, you can boost your reach in distance, okay? So the effective energy scale that can be probed by a collider is not only dictated by its energy, but also by its ability to perform precise measurements of what is produced in the collisions. And proton colliders have an issue that precision is limited by the overwhelming large phenomena that are interesting but are long distance phenomena, so are not exactly what we would like to study, that are difficult to model and to subtract, and these are the QCD backgrounds. So at least generically speaking, it's clear that the muon collider is more precise than a proton collider. The muon collider then is energetic and it is precise at once, okay? So it has advantages, and of course it can also, the right way to say this is that can be complementary to a very high energy hadron collider, and this is the justification for investing in studying the muon collider. Okay. So, in terms of the status of the muon collider, here there is a timeline, and so. First ideas, in fact, on the muon collider, I learned recently that are even before 1980, okay? But so it was really long ago, the idea of colliding muons and the advantages this will bring. And then there's been a long development of brilliant accelerator physics papers trying to explain how you can form a beam out of these muons, what is called ionization cooling, and a lot of developments in terms of concept, okay? There was only a very short period of time where in the United States the muon accelerator program was active, and that was a collaboration similar to IMCC, which is active today, that tried to put all these theoretical ideas together and trying to end up with a start-to-end design. They made a lot of progress, but they were prematurely terminated. And the next point here in this time axis is 2019-2020, where the update of the European strategy for particle physics, so the past strategy, today we are updating the strategy again, the past strategy reconsidered the case of the muon collider. It found that no showstopper was identified. It considered that the progress achieved by MAP was substantial. It also considered that many years after MAP was completed, experiments, okay, components demonstration of different type were finished, were successfully accomplished, which were initiated at the time of MAP, but then they terminated something around there. And so the recommendation for the first time in Europe was to set up a collaboration in order to continue, if you want, the work of MAP for the first time in Europe. And this led to the creation of this logo, which is the International Muon Collider Collaboration, which is active since then. These ones are the target of the IMCC. The The target is a 10 TeV energy muon collider. Without this meaning that we have indications that 10 TeV is the maximal energy that the muon collider could ever possess, okay? But it's just the target which has been chosen by the collaboration, and well, manpower allowing, of course, we should start studying what happens going to even higher energy. There is also a 3 TeV energy market here, which should not be considered an alternative goal, but rather a stage, okay, a possible stage of lower energy towards the goal that is 10 TeV. This is the luminosity target, instantaneous luminosity, and this is very high. I can explain you that it's very high by looking at this formula down here. It's not difficult to argue that for a satisfactory physics program, you should aim at around 10 inverse atom of integrated luminosity for the 10 TeV machine. And well, this instantaneous luminosity here is such that you can, in theory, collect this integrated luminosity by running the machine only during 5 years, okay, which is very short, of course, will run longer, and only with one interaction point, while being a circular collider, you will have 2 interaction points. This is to say that there are perspectives to get higher luminosity integrated if this target can be accomplished. If this target is missed by a factor of few, for example, but even 10, this will change very little, in fact, and would not make, let's say, so the project would still fly very well. So the appeal of the muon collider, of course, is the fact that it is compact, okay? So the biggest ring of the muon collider is the one that is marked here, and it corresponds to the last stage of the acceleration, okay, because the muon have to be accelerated quickly before they decay. And the smallest ring instead is the collider ring, where there is no acceleration, just collision, and it's smaller because you want to have higher frequency, okay? And so you want a smaller ring with the maximal possible field. The muon collider is relatively small in comparison, for example, with the CLIC, E plus E minus collider that will reach 3 TeV, the FCC that in a HH mode could reach maybe 100 or 80 TeV, and the size of the last ring, okay, of the last ring of the last acceleration stage is more or less similar, as you see, with the one of the LHC tunnel, and in fact, it has been studied that successfully there is the possibility to reuse the LHC tunnel for the last stage of acceleration of a muon collider of high energy. Okay. Another interesting thing has to do more with sociology, but it's important. So this plot here shows the evolution of the number of papers on muon colliders since when essentially the HEP-PH category, I think, in the archive was introduced. In blue, you have the papers, in fact, in the HEP-PH category, so about physics, and the total is all papers on the muon collider, which, as you see, most of them are gray, which means most of them are about the technological feasibility, accelerator studies, technology, and so on. And you see that in the past, well, there was not much attention to the physics of the muon collider. There was some interest coming as a reaction to brilliant ideas and developments in accelerator physics, like here, but also some of these peaks, for example, this one, is not really followed, not even by blue peak. It's just a crappy distribution like this. While instead, after the update of the European strategy, so this is 2019, the situation is completely different. The blue paper are not only in an expansive let's say, situation, but also they constitute a almost dominant component of the total number of paper. And this means that apparently in 2019, 2020, and later, there is strong interest on the muon collider, possibly also because the LHC is going to come to completion, and so we have a more clear picture of what is needed next. And most likely, I mean, this shows that a number of people believes this could be a muon collider. Okay, I'm almost done with the history. 2023, there was the SNOMAS MP5 process in the US that introduced this very American notion of the muon shot. Okay, that is, however, an important fact concerning the resurrection of the ambition in the US in the long term to host a collider on US ground, and this collider will be a muon collider. And so with I mean, this is important news for collider physics at large, I would say, and in particular for the muon collider. Last year, or this year, in fact, there was the report from the National Academy of Science that gave as recommendation one the United States aiming again at hosting a very high energy, highest energy elementary particle collider around 2050, which requires the immediate creation of a national muon collider research and development program to enable the construction of a demonstrator. And so to embrace, if you want, this resurrected path towards the muon collider that in Europe we have been working on already for a few years. Okay. The next step will be the next update of the European strategy, which in 2026 will evaluate the outcome of the MCC study, which is essentially a detailed R&D path plan that includes a number of actions. The most visible and expensive of all, of the scale of 100 million, is a demonstrator of the ionization cooling, which is the key innovative technology that we need in order to form this muon beam. It has to be cooled down, which means it has to be brought to have the shape of a beam instead of an incoherent set of particles, which then you can accelerate and collide. Okay? Sure. So each time I try to explain is when there is an accelerator physicist in the room, they correct me. Okay. So and also okay. So this is at fixed field. Okay. This is at fixed field. So a fixed magnetic field, and so it also, so when you see this formula, you also take into account that then the size of the ring is changing. Okay, so it's not so this is the case you get the scaling. To me, my understanding, one of the understandings, but surely some accelerator person will contradict me, is that the muon's lifetime is longer. So one effect that for sure you don't have in a normal collider, okay, is that the muons live longer when they are higher energy. Okay, and so you can collide them for longer. Okay, this is one possible explanation. There is an effect which is at all colliders, which is the reduction of the emit, because when you are very boosted, then of course the angles they all go straight, and so there is one power that I think you can understand from there. Okay. Okay. Yes, yes, this effect is common. This effect is common. So again, since each time I try to explain this, I fail. So I prefer. Okay. Perché? Yes, yes. Yes. No, but this is done a fixed. No, aspetta. This is done a fixed power for on protons. No, fixed field, but also fixed power. So the power of that you put in the target in that estimate is fixed. Okay, which means that if you have a muon that leaves, so once you produce a muon, this costs you a certain amount of energy. Okay, so if the muons live 2 times longer, okay, the same muon makes more collisions. You see, so the source of the muons is sort of fixed in that estimate because it's done a fixed target of proton on power of the fixed power of proton on target. So there is also this effect. No, this is the so there are 2 different things. One is so of course this complies very well with the idea that you want to have a constant number of events, sure, but this quadratic scaling is the natural scaling of the muon collider luminosity from the viewpoint of beam dynamics. Okay, if you keep the magnetic field fixed, and also there is a question about the beta star. So it could be difficult to maintain this scaling at very high energy, okay, because you also buy a more and more ambitious beta star, right? When you take this scaling, okay? Okay, so you're saying sort of yes, so I feel better. Eh? Yes, yes, yes. So, but yeah, so it's a pity I was not there during the first week because I also would like to have a very so instead, in fact, in our towards the muon collider, there is an explanation of that. There is a calculation that I'm able to follow, more or less, but then I'm not able to repeat it. Okay. More questions? But yes, of course, also, as you say, this is great if you can be maintained, because it means that 2-to-2 scattering goes like 1 over e squared, the geometric scaling, which is compensated by e squared. So, yeah. Okay. Okay, so the physics. So the targets for physics at the muon collider, the way we like to expose them is not by making, I don't know, some list of beyond the standard model hypothesis that the muon collider can test, a sort of checklist. Today, we think it's more appropriate, given the large uncertainties that we have to admit in what exactly is that we're looking for. The most appropriate way to illustrate the future colliders, and muon collider in particular, exploration opportunities, is to really focus on methodologies more than on targets. For example, you can make very precise measurements, and this is the precision arrow. Then with these precise measurements, you have to go and you can list which type of question you can answer to that may, of course, include specific targets for physics beyond the standard model. You have energy, which means the very simple fact that now you can discover new particles with presently inaccessible mass. And here I'm emphasizing WIMP dark matter candidates because they still remain surprisingly not yet explored in the most appealing form, which is minimal, if you want to, what I like to call minimal WIMP dark matter, still unexplored option for dark matter. We discussed, already mentioned precision, which includes measurements that a Ni plus C minus low energy X factory cannot do, like, for example, the triple X coupling. There is this arrow here, which is in between precision and energy, which precision from energy, that essentially comes from the opportunity of having, instead of having one collider that is very energetic and one other collider that is very precise, we have a collider that is precise and energetic. And so what we can do, and we cannot do otherwise, is to measure with precision observables of high energy. And this type of measurements are unique of the muon collider. And so they have, let's say, unique sensitivity opportunities. And finally, there is a last arrow, which is in fact very much connected with synergies, that is called here muons and neutrinos. That means two things. One thing is that new physics may couple to muons more than to electrons for good theoretical reasons, or just agnostically. Well, we have checked more what goes on with electrons, less with muons, and so maybe there is just an opportunity by the fact that the beam, colliding beam, is made of muons and not, again, for instance, of electrons. But also there is the fact that the muons decay; they produce neutrinos, which can form a very useful beam of neutrinos with unprecedented properties that can be used for a parasitical experiment. The type of forward physics facility or phaser type of things, so forward detectors, using this beam of neutrinos for other physics applications. Beyond, or if you want, let's say, behind all this, in some sense, there is the fact that using this very high energy and this high precision, we can sort of envisage by this high energy electroweak collider, a unique probe of a new regime of electroweak interactions where you do have a sort of unification between the electroweak and the Higgs. So you observe the standard model in a certain sense in the regime of energies where the standard model is simpler, in the regime of energies where the standard model is really shows its microscopic phase, and so there is also a number of growing interesting to me into trying to spell out what is the physics case of the muon collider and of future projects maybe within the standard model. So let's go through the different items. So high energy, simplest thing, you smash particles, they are heavy, and if the new particles are coupled to the electroweak force, then no matter which other couplings they have, you can produce them in pair by this very simple diagram, and the luminosity that we have is very high, such that you cannot read very well here, but probably you can measure here. So the number of events that you expect for the production of this pair of particles by electroweak interaction is extremely high. For example, this is 10 to the 3, okay? And so you will be able to discover these particles generically by just a few months or less of runs of the muon collider, and also be able, if you discover something, to characterize its properties very precisely, really by precision studies. Of course, up to the mass threshold, which is 5 TeV, okay? It's half of the collider energy. This plot it requires is about WIMP dark matter, in particular WINO and XINO, and it should be outlined not only because these are interesting specific candidates that the muon collider can reach up to this black marked here mass, which is the thermal mass, the one that, if you want, explains dark matter abundance. It's also interesting to show this plot because this WIMP type of dark matter is an electroweak charged particle, so it's produced like this, but then its decays are complicated because of the small mass splitting. There is essentially I mean, the charger component is produced, but then it travels only a little bit, then it decays with very small phase space, so with products that are difficult to observe. And so it's important to remark that these studies, these sensitivity lines, are obtained with a full simulation of the muon collider detector, including this challenging, I will come back to this a bit later, maybe beam-induced background from the muon decay, which in principle could be an obstruction to physics, but this is a very complicated signature that in principle, well, so for which this beam-induced background is in fact not a problem. So this plot is also very reassuring from the viewpoint of the physics and detector performances of the muon collider. Then, okay, this is fine. So then there is also another mechanism by which new physics could be produced, which is vector boson fusion. This is interesting because maybe new physics does not couple directly to electroweak, but if it is connected in particular with the Higgs sector, with the electroweak symmetry breaking sector, for very good reasons, which we could enumerate, you may expect to have particles that couple through the so-called Higgs portal. So they have interaction with the Higgs. And now interaction with the Higgs, it's easy to see that they get converted into interaction with longitudinally polarized electroweak bosons. And electroweak bosons collisions, like this or like this, are extremely abundant at the muon collider. We say that there is there is a regime of collinear emission of these objects, of these say, propagators, where effectively this can be described as the presence inside the muon, okay, of some partons. They were, in fact, present in the plots I showed you before, of some partons that are effectively W bosons. And so you have a lot of luminosity for colliding W bosons because the high energy boosts this collinear emission a lot. And so you have, in some representative model, this is a plane mass versus coupling, you have the sensitivity of the muon collider, and you can check how much it extends with respect to current knowledge, and also how it's very well, so in fact, better is in this interesting region following this line than a hadron collider. So it gives you an idea of the gap in logarithmic scale that there is in opportunities from current knowledge to future exploration of Higgs portal type of new physics. Which can be connected with strong first-order phase transition, can be associated with naturalness in different contexts. So it's an interesting case study. Here there is precision, and one thing has been studied a lot on the muon collider precision is the Higgs. There are 10 million Higgs bosons which are produced at the muon collider, and they are mostly produced in vector boson fusion. So at low energy plus or minus Higgs factory, you have order 1 or 2 millions, I believe, and they are produced with a different associated Higgs production. So this is a different production mechanism that again exploits the large vector boson fusion scattering cross sections to produce a lot of Higgses. And so this large number of Higgs bosons can be studied for a program of measurements of the Higgs couplings that in several interesting cases, it improves the precision on the Higgs couplings by a factor of 10 with respect to the knowledge after projected knowledge after high luminosity LHC, and it brings the knowledge of Higgs couplings to the per mil regime. A plus minus Higgs factory could do something similar, but still you see that there is complementarity in the sense that if any plus minus Higgs factory is built, you will still be interested in measuring the Higgs couplings at the muon collider because this will improve, okay, the sensitivity, okay, in particular to certain couplings. For example, this one you see stays the same in the combination, but also you can access new properties of the Higgs by double Higgs production. Okay, you can access the Higgs trilinear coupling with the precision that at the muon collider 10 TeV is essentially comparable with the best precision we can hope to get, not at low energy Higgs factory, but at high energy plus minus like click or SCCHH that is needed in order to access double Higgs production. To be mentioned also that other processes that could be studied here are not being studied at all, but there is also the muon collider. There is also about more than 100 million W boson produced and Z bosons produced similarly to the Higgs, right? And the opportunities associated with those, in fact, have not been studied. The focus has been more on the Higgs. Okay, so the arrow, this one in between, precision from energy. So here the idea again. Let's take the events that occur at the highest possible energy, for example, the production of two plus minus with an invariant mass which is of the order of the collider energy, something like above 8 eV, let's say. So the simplest process, mu plus mu minus going to two things. What is the possible impact on probing physics beyond the standard model of this measurement? Well, we know the answer in a certain sense. From textbooks, we know that when you try to probe a proton or a nucleon by a scattering of an electron, so by a virtual photon which has an energy which is very small in comparison with the size of the proton, well, this looks elementary. You cannot resolve the finite size of the proton. And in order to discover that the proton has a finite size, you had to wait until when someone was able to engineer electron collision on nucleons at an energy of the order, okay, of hundreds of MeV. At that point, the effect of proton compositeness became evident because this four-factor F is a sort of polynomial expansion in E over lambda, and the first term is E square over lambda square. Lambda is the new physics scale that, in the case of the proton, is lambda QCD, is the inverse of the proton radius square, and so it's only when the energy gets higher that the effect can be large enough to be seen given the finite experimental resolution. And so the idea is essentially here that if you have a new physics scale which is very heavy, around 100 TeV, this new physics, similarly to what happened to the proton many years ago, could be there and could entail corrections that today we cannot see because they scale like E square over lambda BSM square. And so if you make an experiment at around 100 GeV, this effect is invisible because it's 1 part per million, while instead, if you raise your energy to be at 10 TeV, then this becomes percent, which is well, large enough to be seen, at least in line of principle, and possibly visible at the muon collider, given the luminosity it has, and so the statistical power of these measurements. And then by exploiting this energy and precision together, you have, for example, the possibility, if you are interested in a new gauge force with a mediator Z prime that has a very high mass in the ballpark of hundreds of TeV, then, depending on the coupling, here you have the reach of the muon collider, and you see that the muon collider is essentially the only option to probe this hypothesis up to these very high mass scales. Again, similarly to, if you want, this will be an effect similarly to the Z discovery. Also for the effect of the Z, also they scale quadratically with the energy. composite Higgs. So this horizontal axis is the inverse of the Higgs size. So it's the Higgs composite scale. This is the geometric size of the Higgs. And the muon collider can test this up to about 50 TeV by exploiting precisely measurements which are fully analog, in fact, to the measurements that were used to discover the proton compositeness, though turned out a little bit. So with this mediator in the S channel. Okay. So this can also be illustrated. Those probably there are not many, but those of you who like effective field theories, these are interaction operators of different type, and this is a long combined fit that considers a large number of possible interactions. You can view each of these interactions as the possible effect of a new particle with a mass which may be about this is about 100 TeV, that is exchanged to produce this low energy interaction that then we study at around 10 TeV. And you see that the reach is consistently around or even above 100 of TeV, and also that the fact that the reach is, so the shaded reach is the single operator and the solid is marginalized. The fact that there is not a big gap between these two, it means that the muon collider can in fact make a lot of different measurements that are able to disentangle different operators. Otherwise, you will see a huge flat directions that will show up in a global limit that is way inferior to the single operator, which means that the muon collider can make a very complete program of characterization for new interactions of a certain class at about 100 TeV scale. Okay, and again, we can do this by targeting relatively large effects, which are easy, okay, to detect, and also easier to really sure that you have discovered something. Of course, an effect at 1 part per million is more doubtful than a larger new physics effect. Same mechanism can be applied to flavor physics as well. If you have a rare flavor transition, I don't know, for example, a transition of a tau to 3 muon by the decay tau to 3 mu, you can study interactions which have 1 tau and 3 muon, which violates lepton flavor, and this is current sensitivity to the scale, and this is future prospects. At the muon collider, you can also try to see if mu plus mu minus produces a muon or a tau. So you can try to see directly if there is a flavor transition instead of studying it as very low energy. You can study it in scattering with a sensitivity that can be extremely competitive with, as you see here, okay, in terms of the scale, extremely competitive with other probes. And this is, for example, D mesons physics, so transition involving charm up. This is strange down. So we made a long classification of all these different possibilities, finding interesting perspective for muon collider doing flavor physics, okay, but not at the intensity frontier, at the energy frontier. Okay, so muons and neutrinos, I will be brief here also because this afternoon, this is more for synergies, in fact, and so I think this afternoon there will be more about this, but in essence, the fact that muons decay to neutrinos, and so in the straits of the collider, the muons go straight, and so they decay, and they decay. Since they're very boosted, their decay products form a very narrow cone, and so you have access to something which is called a neutrino beam with small aperture, such that you can collect all these neutrinos in some detector placed maybe even a kilometer away from the interaction point, which is from where the muons are produced. And so this gives rise to a collimated and perfectly characterized neutrino beam. I say this because most of the neutrinos we collect in experiment, they have a flux and an energy spectrum that is not predictable, okay? And these uncertainties, of course, have an impact on the physics. In this case, the neutrinos come from the muon decay, so their distribution is completely predictable because we know how the muons decay very well. This plot shows the number and the spectrum in energy of neutrino interactions that you may have at a plausible forward detector. I need to assume some detector because, of course, to tell you the number, I need to assume let's say a target mass and these kind of things. And so this is, for example, what you could expect at the 10 TeV muon collider. In log scale, there is a huge gap with respect to what is known, what we can do today, what even the forward physics facility could do. And this overwhelming number number of TeV energy neutrinos can be used for making measurements, and two examples are here. A fit to the PDF, which is orders of magnitude way more precise than what we know today, the parton distribution functions of the proton for QCD studies, but also a determination of the elements of the Kabib-Kobayashi-Maskawa matrix, which could be more sensitive. So look at this. Look at this line in comparison with current knowledge from the particle data group, but also obtained with a completely different methodology than studying transitions in meson decay and the regular flavor physics. So this will be very interesting also opportunity to be better investigated. Okay. Right. What time is it? Vabbè. Okay, I will try to go faster here. So I like the idea that that the standard model. If you want, okay. So the electroweak interactions, they change phase many times when you increase the energy from below the electroweak scale, at the electroweak scale, and when you go much above the electroweak scale, where we have not yet probed them completely. And one interesting thing is that when you teach the standard model, when you want to teach the standard model Lagrangian, you always start from this part. Okay, you always start from explaining how simple and beautiful is the standard model seen as a nearly massless gauge theory, in which you have the Higgs doublet, in which you have the gauge fields, which are nearly massless, and also you have the opportunity in this regime to explain the most important property of the standard model, which is the fact that it's built in a way that it can be extrapolated up to even higher energy, way down, up to very high energy scales. So the standard model essence at the theoretical level, and in particular the presence of the Higgs boson, is something which has to do with the way the theory works at high energies. In this sense, then, it's true that the electroweak particle, the electroweak boson, the Z, the Higgs shows up at this electroweak scale of around 100 GeV. But in fact, the theory needs it in order to go much above there. And so while it's of course very interesting to study the properties of the Higgs and the electroweak bosons in the regime of energies where you produce them abundantly, like at LEP or at future FCCE or things like this, it's also well, it also feels that the most direct implication of the standard model are at high energies, where in particular you can really see the role of the Higgs as part of the microscopic description of the standard model, which we feel somehow that it should be verified by high energy experiments. So one standard model view on the muon collider physics case is that we will probe a new regime of electroweak force, the electroweak force that is essentially unified with the Higgs. They go together, they are intertwined in a way that you cannot anymore even separate them. And at the practical level, there is a number of things that are cool that will happen at this higher energy, and that we can maybe test at the muon collider because of the precision allows for it. One thing is electroweak restoration. So you will see that the standard model amplitudes, they obey a symmetry, which is SU2 cross U1, which is instead completely hidden by spontaneous symmetry breaking if you look at 100 GeV. There is electroweak radiation, which is essentially a phenomenon that mimics what happens in massless gauge theories, the radiation of W, Z, but even splitting in tops, the Higgs splitting in tops, a number of phenomena that we haven't observed yet, but that we could observe at the muon collider. One may want to check the partonic content of the muon. I already mentioned these effective W bosons hidden inside the muon, but this could be, I mean, maybe really interesting to see if it goes like it's predicted by the standard model or not. Another very cool thing is that because of this effect that, so because of this radiation of soft collinear, soft in particular W bosons, like here, is enhanced because you are at very high energy, then a muon, if you want, effectively at the level of Feynman amplitude can convert into a neutrino, and so you may have scattering, so you will observe the scattering of TeV energy neutrinos with almost 55 TeV energy, for example, neutrino muon or neutrino neutrino, if you emit two of these W. And finally, other things that will be worth investigating in the future are brilliant phenomenological things, like, for example, a neutrino jet, because of this large radiation, this very hard neutrino, which is emitted here and is invisible, well, it will convert, in a certain sense, into a W and to an electron. So neutrinos will stop, to some extent, being invisible. You will have a certain efficiency for tagging the neutrino through this new weird enhanced phenomenon. Okay, so I think this I will skip, just to say that this program also comes with theory challenges that are also practically important for making predictions at the muon collider. This is the challenge of dealing with this large scale separation between the collider energy and the electroweak scale, which makes a big enhancement of these radiation effects that need to be taken into account and resummed. Okay, so this concludes like the physics part. Okay, and so in case you have questions, you can always interrupt me, right? Okay, so in the remaining few minutes, I will go through, without so many details, the principal challenges and the key R&D targets for the muon collider realization. Okay, not being an expert, just having made my best to understand some of these things. So one thing goes within the hat of environmental impact, on which the muon collider is good, very good from some extents, in particular being smaller and less power consuming, plus the fact that if you reuse the tunnel, of course, the environmental impact of the collider will be strongly reduced. There is an important effect that needs to be mitigated, which for some time has been considered a showstopper to the muon collider, so it's important to discuss this, which is again associated with the effect of the neutrinos from the decay of the muons. And it's important to stress that for this problem, the studies of the muon collider have identified a solution that essentially supposedly make that this problem, we can forget about it after we have solved it, that makes the environmental impact negligible. So what is the story? The story, the most problematic part of the story comes from the arcs. So before we had the neutrinos in the straight section, now we think to the neutrinos that decay, the neutrinos that come from the muons that decay in the arcs, and this one makes this collimated beam of neutrinos that does not point always in the same direction as the beam turns. Then it makes a sort of donut, okay, of emission like this, which then can exit on the surface of Earth. So these neutrinos are not dangerous. I can stand in front of this neutrino beam as long as I like, and they will not do anything to me. What is potentially problematic is the fact that these neutrinos, they will interact with Earth in the last around tens, maybe, or more of meters before they reach me when they are coming from the collider, and this makes a showering in Earth, a number of processes that build up some amount of radiation, which again is not dangerous. Okay, if I pass by, if I stay a couple of hours where there is this neutrino beam coming to me, nothing happens. But if integrated on a sufficiently large amount of time, you can go above this legal limit of 1 millisilver per year, which is not so, which is a limit which is soft in the sense that you could be approved, but you need an approval if you pass this limit. Instead, there is another limit, which is this 10 microsilver per year, which is a different thing, which is the threshold below which you don't have to ask for any approval, because this threshold is considered to be a negligible correction to natural radioactivity. Okay, and so this limit of radiation exposition to the public, okay, is something that all colliders have to comply with, and of course the LHC demonstrated to comply with that, and the muon collider will have to demonstrate to comply with this limit as well. Okay, so the promise, okay, as I said, is that we don't have to worry about this problem neither at scientific nor at the sociological level, because there will be nothing to be approved concerning this neutrino possible issue. And the solution has to do with movers. So there is mechanical movers that twist the beam with a long period, because the problem, as I said, is not instantaneous. So it really takes time before you have a problem. And so around, with the period of the order of minutes, you move the beam, okay, by a little bit, okay, in a way that since at different times the beam shape has moved, then the angle emitted by the neutrino is different. And so essentially you spread out in the horizontal direction this possibly narrow beam, and you make it become at surface really large, because you have to imagine that the distance between the surface and the point of emission can be easily ordered hundreds of kilometers, okay? So a very small angle of deflection here corresponds to a huge impact at surface. And so there is ongoing studies of including this mover system engineering, studying the impact on beams, and this solution seems to be demonstrated. Another thing that was considered to be problematic for the muon collider was the possibility of doing physics at the main detector. And the reason, again, is that the muons decay. And as the muon they decay, they do among the other things that they do produce electrons. These electrons go on the beam pipe, go on the elements of the collider, and at some point they also reach the detector. Okay. So this beam-induced background, again, used to be considered problematic, but the reality is that nobody had looked into that until recently, until around 2020, 2021. And even with very simple detector design and with very simple strategies of reconstruction, nothing that requires extremely aggressive technologies, one can do physics, one can reconstruct basic objects, one can do the physics, which of course doesn't mean that the performances are already perfect, but it means that a reasonable goal at this point is to bring the effect of the beam-induced background to disappear, okay? And so far we have two detector concepts that have been studied at the muon collider and that are making more and more study, more and more refinements. And so even if the path has just started, the important thing is that as demonstrated, for example, for the first time in the IPJC report, it's fair to say that the beam-induced background is at least under control, and better performances are surely expected to come in the future as the work continues. Okay, maybe I will skip this. There is a lot of work, of course, probably the majority of the work has to do with the cooling of the muons, which is done by this process that is called ionization cooling, and it's a very new thing that needs to be demonstrated. And so the main, if you want, the main element of the future path towards the muon collider is to build a demonstrator facility, a cooling demonstrator facility that wants to go way beyond what already has been demonstrated about cooling on a smaller scale. That was the mice experiment that was completed a couple of years ago, officially completed a couple of years ago. But also there is a number of things which have to do with RF, which have to do with the study of the proton beam and the test of the target, because in essence the muons are produced from proton on a target, which then gives pion, and then the pion gives muons. And so in this long chain of the muon collider, there is a lot of physics of all possible different types that include also targetry studies. It includes, of course, the design of magnets of very different type, large bore magnets in synergy with fusion, plus of course the collider magnets. And so many of these studies can easily be developed even outside the demonstrator facility, like prototyping of cooling cells, building several components. And so the R&D program of the Muon Collider is not only the cooling demonstrator facility, and it's not only the science studies that you can do on paper, but it's also really technology demonstrators that in principle even small scale labs could individually afford, okay, aiming to, so for a small scale project that however aim at a global assessment of the Muon Collider. Okay. So, in conclusion, we like to define the Muon Collider as a high-energy electroweak collider. Okay, electroweak here is synonymous of lepton, but it emphasizes the fact that studying electroweak interactions at the highest possible energy is the most unique opportunity that is offered by the Muon Collider with respect to anything else. It gives unique access to the simplicity of the standard model in the new high energy regime. It gives unique promise for conclusive exploration of physics beyond the standard model. And as we said several times, it combines energy with precision and gaining more than just the simple union of precise measurement or high energy for discovering particles. And there are a number of unique physics opportunities that I tried to spell out. The effort on the Muon Collider is progressing, so we are starting from very solid grounds, and the center, okay, today of Muon Collider progresses is Europe, and we must emphasize that this came thanks to the last strategy recommendation and thanks to an extraordinarily quick ramp up of expertise, because for like 4 years ago, nobody in Europe knew nothing about Muon Colliders, while instead now there is a collaboration that is actively working and making progress. And also there is key competencies in the US from the old MAP memories that will re-enter after the implementation of the recommendation of P5. And so the perspective of boosting this activity, at least in terms of people working on that, I think it's great. We will see what the strategy considers about the detailed R&D path plan that the IMCC has proposed, which brings us, okay, hopefully, just a few years away from establishing the feasibility of the Muon Collider. Okay, so we cannot say that the Muon Collider is feasible, but we can say that maybe in a few years we will know for sure that the Muon Collider is feasible, and this will be very exciting. Many people work on the Muon Collider, including in the physics and the experiment and detector. And why it is so? Well, the reason is that it's new. Will be the first collider of its species, which poses challenges and opportunities, first of all, in all areas of accelerator physics. There is plenty of synergies, technology synergies can be spelled out with fusion and with many other things that the collaboration is actively pursuing, and also an opportunity for new ideas and new enthusiasm in the area of physics, experiment, and detector, because I think it's a fact that scientists like working on what is new and difficult, and this is an opportunity for collider physics at large, on top of being an opportunity to get ready to assess for real the feasibility and the exploitability for physics of this very high energy Muon Collider. And this is all what I have. Thank you.
So thank you, Andrea, for this very broad overview on the motivations and the physics of the Muon Collider. There were already hints to some possible synergy. I wanted to advertise that on this fact of neutrino beam, there will be a talk on Thursday afternoon. The speaker is not yet here, but there will be a talk. I actually had a question on maybe if you wanted to explain it broadly, just to make a more clear what kind of things can be done once you have this kind of new tools. But first, if there were other questions or curiosities from the audience, I will give precedence to that.
Good morning. Thank you very much, Andrea, for the talk. Keeping in mind what has been discussed in Venice at the European Physical Strategy, I was just asking myself if you can try to summarize the few statement in terms of having in mind a table comparing, for example, what can be done with FCC and what can be done with muon colliders, both in terms of, I would say, three things: physics, then technology challenges, and then finally the time for delivering the machine that you want. What do you think at the end is somehow the ingredient that is pushing somehow the community to say, let's go first with FCC, but keeping the R&D program of muon collider ongoing to a certain point, deliver also that? Well, I know that it's probably quite big.
Okay, if I forget something, you remind me. So if I forget something to reply to something, you remind me. So starting from the end, starting from maybe, yeah. So one clear mistake that was made over the last, I think everybody realized that over the last 30 years, and this was realized also in the last strategy update, is to stop the R&D for the very ambitious future because we have some running project. Okay, the fact that for example, in the US, there is no accelerator physicist allowed to work on high energy accelerators because this was stopped in the US. In Europe, we have very few accelerator experts, and they are always treated like technologists that should implement some decision. This was a mistake, and the last strategy already recognized that this was the mistake, and in fact, it encouraged this laboratory director group initiative the muon collider is part of, is precisely going in this direction. So we shouldn't not even consider the possibility of stopping investing on the ambitious future, regardless of whether we want and we decide to approve a project. And the FCC, in particular the FCC EE, is not the ambitious future, in the sense that it's great, but from the viewpoint of beam dynamics, from the viewpoint of accelerator technologies, from the viewpoint of like accelerator physics, it simply doesn't pose enough challenge to maintain a community alive for 40 years. So as far as it goes, in fact, development of the muon collider is very synergetic with the fact that really we have to implement FCC, right? So we need people. Not today, we need people when we will need them, right? In many years from now. So we don't put them in a box and then hope that you open the box and they're still alive, right? You have to give them challenges, and of course, plasma wave field acceleration, which is doesn't have a clear path like the muon collider. The muon collider are exactly the arenas where these people will flourish and not only survive until the next project. Okay. So this is part of the answer. The muon collider has also in comparison, even with the FCC-HH, that has its own challenges. Unlike FCCE, these challenges are relatively limited. High field magnets. Okay, the muon collider needs high field magnets, which must be developed, of course, in synergy, thinking also to a proton collider. But it also needs RF. It also needs energy recovery for the fast acceleration. It needs this large aperture solenoid for capturing the pion from the proton. So it needs many more different technologies. Okay, it needs it's much broader. Okay, and also it's much broader, and also it's in some sense more innovative. So it's not by chance that we have all these synergies with fusion, this new grid stabilization. So I think it's, I mean, I'm not the right person to defend the case, but to me it's evident that it's incomparably more rich, the R&D program of the muon collider, with respect to what you have to do today for any other future collider project. In terms of physics, maybe you wanted to know about FCC. So with respect to there is a couple of unique items of the muon collider. Okay, well, that all somehow build around the fact that you can have high energy electroweak processes that are studied precisely without UCD background and at very high energy. Okay, so there is a number of physics that you can extract from there, and you can extract from there better than other probes. And there is concrete, let's say, aspects. I don't know, for example, if you want to study the production of electroweak charged particles, the reach will be higher at the muon collider than at the FCC-HH. Okay, it will be the other way around if you're interested in particles that are only QCD colored. So there is complementarity between the physics case of the muon collider and the whole physics case FCC plus HH. Or even if you tell me that you really have decided to do FCC HH, and I will disagree with you because FCC HH is something that may get so long and so far in time that is not worth discussing. We can definitely so there would be a case for building a muon collider even there. The hope is that the muon collider could be built earlier, because in terms of technology limited timeline, with this timeline which has been shown, so technology limited means I mean, doesn't mean the timeline of the project. Okay, if no one is going to get money, give money to you, then this timeline can be extended infinitely. Okay, so it's an estimate of what will be needed to get the technology that you need for building a project that, in line of principle, could, as you see here, okay, start running around this date, okay, 2050. Okay, but what we care is what happens here. Okay, we believe that in the next 10 years, without interfering with nothing else, we can do brilliant R&D, brilliant developments that first we need to establish the feasibility of the muon collider. Did I manage to answer more or less to a good fraction of your questions?
Yes, thank you.
Let me mention one thing, which is maybe partially going in the same direction. This technology R&D are, of course, a minor fraction of any development of any collider project that will happen, will be approved maybe soon. So in the spirit, I think I can summarize Andrea saying you don't have to stop any R&D just because you have a project, and maybe it was a mistake in the past to kind of tone down these R&D projects. Even at the level of costs, so we are discussing completely different scales. So it's important to keep in mind that while there are very ambitious R&Ds, they are not collider size expenses. So in this sense, we can be also exploratory. And that's one of the goals of the week, in a sense, that since we allow ourselves to be exploratory in the R&D phase, precisely because it's R&D, one can even imagine to have more demonstrators, for instance, than what's technically needed to demonstrate the muon collider needs per se, to change the plan, to include some physics that can be done only once you start modifying these R&D paths that have been so far only focused for muon collider purposes. So yeah, exploration of this aspect is one of the things we want to do this week.
Thanks for the interesting talk. Could you go to page 28? I think 28 or 7, I don't remember.
28.
20.
Sì, no. Okay, 28.
Yeah. So here, could you clarify? So you are using neutrino and the proton collision. So where does the proton come from? You have another.
No, sorry. I was fast because then Yuichiro told me that he will speak about this in the afternoon. But I'm talking about an experiment in which. So how should I draw it? Okay. So, okay. Okay. So this is the collider. So there is a far forward detector. Okay. So the collision are between these neutrinos and the material that makes this target.
So that is fixed target experiment.
It's a fixed target experiment.
And okay, so could you go to the page before that?
Page before that.
Yeah. I was just a bit confused because you write like in the plot you write like a 10 kilo or whatever.
Yeah.
That's the mass of the neutrino. Is that the mass of detector?
The mass of the neutrino probably not a kilo.
I see. And
no. So I tell you how is that. So this 10 kilograms. So this is marked 10 kilograms because so this has been done using a concept of a neutrino detector that was built in long ago in the context of the map studies, which in fact has a target that weighs 10 kilograms. Okay, so in comparison with neutrino detectors that people does, this is ridiculously small. Okay, and so we felt that it was legitimate to scale this up by a factor of 100 by a 1-ton detector. Okay. Now there are several things that what we will say about this, in the sense that this also is based on a very conservative estimate of the flux of neutrinos, and also, but anyhow, so I just wanted to emphasize that this 10 kilogram line is there because it corresponds to an existing detector concept, not because we believe that this will be that this is particularly realistic, because the detector is very small. Okay. So
may I understand this is the mass of the detector you just draw on the blackboard?
The mass of the sorry, what do you say it again? The mass,
is
the mass of the target.
Yeah.
So this target will be something like 10 centimeter radius. Okay, and then with certain length. Okay, here is 1 meter in this design, which then we'll have a certain density. So with 10 centimeter, you sort of intersect all the neutrinos. Okay, and so then the only thing and then in this setup, the number of interactions just depends on the total mass of the detector, which is its density and its length times its length. You see?
I see.
Okay, so this is effectively like having a rho L, which is 10 times rho, rho L, the parameter that, anyhow.
And then typically, like, how far away you need to put this, like, back to.
Yeah, so could be a couple of kilometers.
Kilometers, like not like a few hundred meters is.
Few hundred meters will not work because the strait in the current design is 500 meters long. So we should better place it far away. And so the statement is that if the neutrinos come from a region in the straight section, and it seems that there are, where the muons have a very, very small angular spread, okay, then the opening angle of the neutrino beam is super tiny, like 0.03 millirad, okay? And so the opening of this cone is such that you will have this 10 centimeter radius, say, cross section at about 2 kilometers, which is safe.
From 2 kilometers.
Yeah.
I see.
Which is safe from the viewpoint of the possibility of installing this detector. But no design has been made. There has been some simulation from the beam people trying to look at the spectrum, sorry, the angular spread of the angular distribution of these neutrinos, and more or less they comply with this type of naive estimate I'm telling you, okay? But there is no study of detector, so it's something still preliminary, but it doesn't look particularly challenging, at least to collect all these neutrinos.
But this is a circular collider, so that means you can put like several different targets in different directions, right?
No. This one now I'm speaking, sorry, it's a bit, I should do a better plot. So this is straight section. So the neutrinos which are useful here are those that come from the straight section of the accelerator, because they all go in the same place, such you can collect them.
So the straight section is a part of the ring, or it's just an additional part of
will be the interaction region.
Ah, I see. So that's the interaction point. The straight sector is the interaction point, right?
Yeah.
From what? To be safe from what, though?
No, because in the current design, if you look, the straight section in total, okay, this is the IP, is 500 meters. Okay.
Yeah.
And then, of course, I cannot put a detector here, right?
Sure. Okay, fine. But I don't see why it needs to be multi-kilometer necessarily.
Okay. If you want it to be well above 500 meters, 2 kilometers qualifies.
But I
mean, I think you want to put it wherever the beam comes out of the earth, right? That's where you want because
no. Should be underground.
Well, I mean,
must be underground because otherwise
okay. Those spots from the straight sections are not safe. Like they're not below background radiation. So part of the point was to create a controlled area you know, part of the point was use a neutrino facility so that you could like create a practical controlled area.
On the surface.
Yeah.
Okay, but this is not the right physics case, because on the surface, this beam, so the angle is tiny, but after hundreds of kilometers, of course, it became too big.
It depends if you're tilted at all, right?
The exit point, for example, for the CERN design is on Jura, so no way.
But similarly, for that small angular spread, where's that number coming from? Is that true accounting for all of the optics along the entire straight section?
The number, the second small number I mentioned is just the intrinsic spread that comes from the decay of the muons.
Okay, but then yes, right. You have a final focus which has some.
The final focus has much 0.8 millirad. So the final focus region is not good. It's not good because this has this large angular spread, and so you will need to pay. So this 10 centimeter radius thing should stay 100 meters away, which cannot be because of this.
But then even for the entire straight section, though, I mean, you have some optics that are.
If you look at the plot of the angular spread in the straight section, there is multiple regions where the beam is in fact made to become large, well, relatively large, and very, 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 very parallel. Okay, very small angular spread.
Right, that's exactly what I'm asking.
But that regions are those that I think will contribute most to these useful neutrinos.
I guess I just mean you mentioned this kind of 10 centimeter diameter or something like that target, and that captured the neutrinos you're interested in, but does it capture all of it given all of these angular spreads?
That's what I'm saying. The neutrinos that come from a straight in the accelerator, so the neutrinos that come from a region where the angular spread is of the order of 1, sort of like 10 to the minus 5 rad, sort of. Okay, those ones, all of them intercept this thing.
Sure. What fraction is
so
that's
in this estimate, that's one of the reasons why it's conservative. It's considered that only 1 meter of the straight section, 1 meter of the entire section is in this favorable condition.
Got it.
So that's one of the reasons why I'm saying that this is very conservative, because in fact we don't know. But the plot that we have now, the straights, it could be I don't know, even 50, 100 of meters of this 500 meters where I do see an angular spread that is like very, very small.
It seems like we have all the numbers to then just actually.
So Daniele will do this for his thesis.
Okay, yes, exactly.
He has done this already, but he will redo it with a new lattice.
So for a second, if we forget about how long this straight sector is, may I ask if farther away the better or the closer the better for the detector?
So in line of principle, the closer the better, because you can make the target region smaller. There is no problem of pile up. So the density of interaction is so small that, I mean, the limit, so the closer the better, just because the detector, so the target can be more compact. I don't see any problem in making a target like this or making it smaller. So to what extent is an advantage, I don't know. And I don't know of any other reason. Maybe some radiation, maybe some radio. So we also have to make sure that here you don't get some background, right, from the collider. So that's maybe instead the reason for willing to put it farther away. But
So the 2 kilometers is the most possibly allowed minimum distance.
The 2 kilometers for 10 centimeter is the minimum distance, because like the beam cannot be smaller than this.
But at least you can put like also one detector on the other side, right? You have the straight sector, you have one side, one detector, the other side also one detector.
If you want to collect both charges, then you need 2 detectors, yes.
Okay, thanks.
And an entire talk for the neutrino exactly on this one Thursday.
Good.
I don't see other questions, so thanks again, Andrea.